Next up, we're going to hear about Nest automation infrastructure from Usman, Giulia, and Sam.
Those little things, clinging to walls, clickety-clacking in corners, appliances from another era. Things that go in the night. Kinda ugly, kinda dumb, which is a little sad. Because all those little things are too important to go unnoticed and unchanged year after year. But we noticed them and thought maybe they could notice us. Because your home should know when you're there and when you're not. Know that you like it cool in the morning and cozy at night. It should give you a
heads up
when something goes wrong or when someone's at the door. So no matter where you are, you'll know everything's okay. What if all the things in your home worked together? Your home could start taking care of itself and take care of you. So you can focus less on little things and more on the things that matter. Nest. Welcome to the thoughtful home.
My name is Sam Gordon, and I'm joined on stage today by my colleagues, Giulia, Guidi, and Usman, Abdullah. And we're extremely excited to talk to you about some of the automation tools that we've developed at Nest. Specifically, we're going to talk about some of the more universal cross-product, cross-platform tools that we've developed as they relate to sensor emulation, data injection, and power analysis. And then we'll take a little bit of a technical deep dive into some of the more device-specific or feature-specific tests that we've developed as it relates to motion detection on our camera. It's a lot to cover, and we're very excited. But first, we're going to give you a little bit of an overview of who we are and what our vision is for the thoughtful home, as the video mentioned. Our first product, the Nest Learning Thermostat, is an intelligent thermostat that learns automatically what temperature you like your home. It learns when you're home and when you're away, with the ultimate goal of saving you money and keeping you more comfortable. Our second product, the Nest Protect, is a smoke and carbon monoxide detector, has a dual wavelength sensor that detects more fires faster, and it uses voice alerts and connected smartphone app that is much more user-friendly than typical middle-of-the-night chirps. The Nest Cam is our wireless IP camera solution that is truly your eyes and ears within your home when you're away. And it comes with an optional cloud video recording service that enables you to relive those special moments for up to 30 days. Lastly, there's the Works with Nest ecosystem, where Works with Nest devices contribute data and connectivity to other devices within your home. So your Philips Hue lights may turn red when your Nest Protect detects smoke, or your Nest Learning Thermostat may start adjusting your house to your optimal comfort temperature when your car lets us know that you're on your way home. All of this sounds great, but there are many challenges associated with building these devices. First, there's a multitude of coordinating sensors that provide data both to the host and to the cloud services. These auxiliary sensors and radios must fit in a similar form factor to traditional devices so that they feel familiar within the home. Many of our devices are battery powered, and they must last for months or even years on a single charge, making power management a critical item. Lastly, Nest strive to build best-in-class devices that also provide connectivity and data to other devices within the ecosystem within your home. Presents a unique challenge for us. And we overcome these challenges through a rigorous testing paradigm. We have form factor device racks that are constantly running new software. We use environmental chambers to test our devices in different environmental conditions. We run device simulators that run software regressions on a PC or in the cloud with no physical hardware required. We use sensor emulators to inject test vectors directly into the device's microprocessor while also running production software. We use real-world data injectors to play back samples from devices like the Nest Cam. We run power and functionality regression tests on daily builds using continuous integration solutions. We run full suite regression testing on potential releases. Lastly, our beta testing program, dubbed Field Trial, is truly the last check before a software build is blessed to go out the door. And all of these fit into 3 different testing methodologies. There's black box testing, where we test the device without any knowledge of the algorithms running on the device. There's gray box testing, where we test the device with a general idea of the algorithms running on the device. And then there's white box testing, where we test the device with knowledge of the exact source code running on the device. And we're going to talk a little bit more about that last bullet point, sensor emulation and data injection. So the question was really posed to us, how do we test the algorithms on an intelligent thermostat from a lab environment? How do we emulate an icy cold winter in Ottawa or a hot and humid summer in Houston, all from an office in temperate Palo Alto? And your first thought may be, well, throw it in one of those environmental chambers you just showed me. But I would argue environmental chambers are not scalable. They're expensive. They require frequent maintenance. They take up a lot of space. And I'm sure there are more things. So taking a step back, let's think about what are the sensor inputs that might be useful for an intelligent thermostat. Well, obviously it needs to know the current temperature within the home and the humidity within the home. Probably should know the HVAC system that's installed in the home. It might be useful for it to have a weather forecast for future temperature predictions. Lastly, occupancy, whether or not anyone is even home at all to heat or cool the home for. And we developed the Sensor Simulation Board, which is a microcontroller-based platform that we use to simulate sensors and monitor outputs. And we do that by switching out all of the sensors on the device and talking directly to the microcontroller. We use it to find software regressions and validate algorithms. And we found that it is capable of emulating most of the sensors required by an intelligent thermostat. And it does that using 2 microprocessors and lots of interfaces to the device under test, over 200 direct connections, and lots of standard communication protocols, SPI, I2C, and UART. And on the software side, we write sensor models and device drivers all in our free RTOS application software that uses a custom USB messaging protocol to communicate to the host. The tests and data collection are all being run on the host in our custom Python test framework. And our next question was, how extensible is this platform? Can we also apply our learnings from the Nest Learning Thermostat to our second product, the Nest Protect? So you'll see a couple familiar sensors, temperature, humidity, and occupancy, but there are also some new faces. Now we're concerned about smoke, carbon monoxide, and we have a push button to hush alerts. You may be surprised to learn that, yes, we found our sensor simulator board is capable of emulating all of the sensors required by a smoke detector. And even better, it's capable of monitoring device outputs, so we can verify that our LED light ring is alerting users when something's not right. We can validate that our speaker is providing those vocal heads up or encouraging users to evacuate. And we can ensure that the alarm sirens to wake everyone up in case of an emergency. Now Giulia will come up and talk about power analysis.
Hi everyone. So you might wonder, why are we talking about power analysis in a test automation conference? Well, power analysis for embedded system is really important and it's really useful. First of all, let's take the example of the Nest Protect. With Nest Protect, you have to run for multiple years on 6 AA batteries. So in order to do so, you need a good battery life estimation. And if you have real data, then you can have a very accurate estimation. So you can manage to run for those multiple years. But with power analysis, you can also validate some component specs. So let's say you have a microcontroller and you don't want your microcontroller in sleep mode to go above a certain current. Then with power analysis, you can make sure that it never happens. And last but not least, you can look at your software performance. So if you look at the graph here, you see that different builds have different average current consumption. So we run the same test, which is rebooting the device, pairing it, and we look at the average current consumption over time. And we can see that some builds make the average current consumption way better, whereas some other break it. And when you see that it breaks it, what you want to do is come back to your software and fix it as quickly as possible. So let me give you an overview of how we do power analysis. Well, for electronic system, power is simply voltage times current. Voltage, well, we use an analog to digital converter. For current, it's trickier. So we decided to go with the Ohm law, which states that the current is proportional to the voltage. And the factor is simply the resistance that you put in your circuit. But you can imagine that for us, we want very small currents, a couple of microamp. And we also want to go to a couple of amps. How can we get that with only one resistance? Well, we need to switch from one resistance, and we need to do that in a smart way. So we develop what we call the automatic gain control. And thanks to that, we achieve precision of 1 microamp, the base case. We also wanted to measure the voltage because we want to have true power consumption. And we do that at a very high frequency, very high sampling rate, so that every microsecond we know what's happening in our system. So we have two different types of power analysis. You can look at the whole system, it's what's shown on the picture here, or you can look at a subsystem. Subsystem is you isolate a component. So let's look first at the whole system power analysis. So what we developed is a companion board. It supplies a voltage to your device under test, and at the same time, it records all of the current that is and the voltage that is required by your device under test. And you can stream the data to see it live. You can choose to store it on an SD card, or you can even send it to the cloud and retrieve it later on. So the system architecture, you have this power stage, as I mentioned, that is adjustable so that we can use the same board for all of our devices, creating a platform, a reusable platform. Then we have this RSense that you see, which is the automatic gain control. We take the voltage, we amplify it, we do all of the measurement, and then we send that to a processor. In our case, it's a Cortex M4. And of course, we have all of the peripheral for communication and sending the data. So here's the board in action. You can see it, as I said, a companion board, so it's standing by, in this case, the Next Protect. And we have those racks of devices running the same test suite. And what happens is, if you see, when you look at the current consumption, the power analysis, if you see some discrepancy, as the test is exactly the same for all of the devices, you can look back into the log and understand what's going on in your system. So you might wonder, well, what does it look like? Let's take an example, the nightly promise. So what happened during the nightly promise is you're home, it's night, you turn off the light, you're gonna go to bed, and you want your Nest Protect to check on its sensor and its battery so that you know it won't wake you up. And the device itself, it's gonna tell you that everything is okay by turning the LED ring green. So what happens when you turn the LED light green is you have the microcontroller, the MCU, that wakes up, and you can see it, it's the first peak that is here. And then you have the wave that you see on the graph, which is the PWM, the command that is sent to the LED. But you can wonder, how do I know that the first peak is the microcontroller that wakes up? Well, because we have this subsystem power analysis. So what it does is, let's say you have your device under test and you want to isolate a subsystem. The subsystem can be a sensor, it can be a communication chip, a Bluetooth, a Wi-Fi, it can also be a microcontroller, and you have a measurement board that applies specifically to the isolated system. And then, of course, you can get the data back. So what we developed is this small board. It's like this size, very small. And it has 4 different channels, meaning that you can sample 4 different subsystems simultaneously. And it's strictly equivalent to those 4 digital multimeters stacked together. So you can understand that for our engineers, when they're running some tests, they would rather use this small board on the desk than this huge stack of lab devices. But for us, it's also way better in terms of cost, because this board is only 1/10 of the price of those 4 lab machines. So we use it on our development boards. The development board is simply the form factor device, so the device that you see in your home, but the electronic is spread out so that it's easier to test it. And as you can see, we have standard headers. They were highlighted in red on the picture. And we just plug our board, and we have the data. Let me show you a video of what's happening. So we have the console on the right. If you can play the video, thanks. So we have the console on the right. You're going to see that I'm inputting commands to the LED and to the Wi-Fi, and the top chart is simply the battery power. You can see the LED 1, which is channel 3, and the Wi-Fi on channel 0. And when I pulse the LED and at the same time do a Wi-Fi scan, you can see that it adds up on the top chart. And also, when you change the LED wave, you can see the current pattern changing. So you can have a lot of information of what's happening in your device. And when you want to test, you can understand that it's really important and it can be very useful information. And yes, the scale is dynamically changing. So that's all for power analysis. Thank you very much. And now Usman is going to talk about motion detection.
Thank you, Giulia. So if some of the hardware talk caught you off guard for those software engineers, the motion detection is going to be more of a software challenges that came up. So I'm Usman. I work on the NestCam team, in particular the motion detection. Currently working on making the motion detection experience as awesome as possible. And hopefully you can buy one of our products. So the NestCam, as Sam had mentioned earlier, is your eyes and ears while you're away. It's designed to watch out for your home and family, even when you can't. It's there to alert you when things go wrong. But coming on a softer side, it's also as a baby monitor, which records all those funny things your baby's doing, or those unexpected dad of the year moments that happen. But the best part about it all is the fact that the NestCam is there to let you know when things go wrong. We have this sophisticated motion detection alert system, which is our key distinguisher between the rest of the products. So the peace of mind that the NestCam provides you starts on our sensor and ends as an alert on your phone. The NestCam has sensors. It's got an on-camera motion detection alert system, which for me personally sends me an alert every time my parents leave and enter their home, which allows me to, from the comfort of my bed, say good morning or good night to them using the built-in speakers and microphone. We also have advanced algorithmic analysis that's done in the cloud, which has a precision and recall curve, which is our secret sauce. So for those of you who might know in pattern recognition, there is a PR curve, which says, hey, of all of the false positives, how much do I want to miss? And do I give you all of the catches of the motion and all of the false positives as well? It gets a little confusing with precision and recall. But in summary, what it means is the motions that I catch, how much of those are relevant? So we do all of that filtering in the cloud so that we don't unnecessarily annoy you every second, every time the tree moves. Then we also have a motion clip storage where you can go back in history and relive and cherish your moments. So I'm going to walk you through an example of what happens when things actually do go wrong. What happens when a burglar comes into your house? Well, first up, some unwelcome visitors decide to drop in, and you're sitting comfortably in your room. How does the NestCam behave? First up, the NestCam sensors immediately detect there's something up. It passes on to the on-camera motion detection algorithm. Says, hey, motion detection, check this out, what's up? The motion detection algorithm runs a light version of the cloud and says, hey, this is something of interest that the cloud should look at, and uploads the data to the cloud. The cloud runs those sophisticated motion detection algorithms, machine learning, neural networks, all that jazz, and sends a notification, yes, this is something of interest to our user, and immediately sends a notification. The user instantly gets an alert saying, hey, there's some sort of activity that happened in the living room, and is able to view the clip. The next is either a 911 call or you chasing your visitors out. All of this magical experience that Nest provided has a lot that goes on behind the scenes. And I'm going to talk about some of the challenges in even testing this. The first step was the entire end-to-end pipeline list, right from the sensor to the hardware, to the interaction between the cloud, to the notification on your phone, and to retrieving the video clips and alerts. the entire pipeline was touched. So if any one of those mess around, you won't get this alert, and this experience won't be as seamless and smooth. So the first test is to make sure that the entire pipeline is tested. And we need a scalable way of testing each and every one of those every time any of the algorithms, sensors, hardware, software, anything changes. Then the second question comes about reproducibility of the scene. How do I reproduce this exact burglar scene in the same light conditions? Obviously, I can be hiring actors and having script this, because I wouldn't be standing here, I'd be directing a script. Then comes the question of repeatability. How do I repeat this 10, 20, 100 times in a scalable way? And then if something happens, let's say at sunrise, the camera messes things out on sunrise, how do I bring in 20 sunrises in a day? I can't be standing out there every sunrise for 10 days and repeating the scene. So all of these challenges were overcome by building in-house solutions. We created a simulated TV testing setup, which gives us free repeatability, reproducibility, and gives us system performance metrics that we can just run on continuous integration. Some of the things that we can automate, such as night vision on a TV, we have to sometimes manually do. And we're currently in the initial phases of bringing in robotics to help us out. So if any of that interests you, come talk to us. We also have simulators, which simulates the camera, because sometimes you don't want to run the entire pipeline. The precision recall curve I talked about earlier in the cloud can just inject in camera simulated data instead of having to go through real life scenarios. The algorithm characterization testing, it's just a fancy word for A/B testing, which we also developed in-house, because this is not your regular A/B testing. It's not just a functional pass or fail. You have to measure what's better in a very subjective manner. And then the user experience. How does the entire end-to-end motion detection experience compare with our previous builds? You don't want to be notified every second. So user experience is also key for the motion detection. The simulated TV testing, as expected, is a camera placed before a TV. We have real-life UART cables coming out for real-time logs. And we place multiple of these to ensure consistency across our devices and to make sure that the field of view doesn't mess around with motion detection in case a user wants to put it in a different angle, different location. The simulated TV box element setup, the skeleton code is kind of something like this. We go out and first of all see what the limitations of our code are and what the limitations of our field are and what our users expect. What sort of scenarios do they expect? Indoors, outdoors, with pets, without pets, duration of events, how quickly, cars, lights, shadows, all of that. So once we come to terms of what our success criteria should be, we go out and record high-resolution videos of those scenes, and we store them in the cloud. But we also curate those data. We label them as indoor, outdoor, light conditions, number of events, duration of the event, what time does the event start from the video. And we have that stored in the cloud so that when we want to, for example, change anything on the camera that says, hey, that should only impact indoor scenarios, or that should only impact small distant objects, or just animals or cats, dogs, we can quickly run just those subset of the videos. If you want to run an entire regression suite, we just play it throughout the entire regression. We play those videos on the TV screen, and the camera sees this as if it were in a real-life scene. Though some people might say, hey, this is the field of view, the frequency, but we'll come to that. So the camera plays it in a regular manner and streams the video as it would in real life. And we can see when the notifications came in, what time the duration came in, how long the event was, what did it detect, what did it miss, all of that. And if anything went wrong, we have smart email and text notifications that come on your phone that, hey, because the entire pipeline, if the server was down, it gives you a notification, hey, server's down, you might want to fix that. So we don't wait for a whole week or days before we come to that conclusion. If I want to isolate the entire pipeline, I just want to check the motion detection on the camera, I can use the same setup. I can see what time the motion event happened, how long the duration was, based on my expected result. If anything fails, we can quickly dive into it a bit more deeper. So what has this helped us uncover? Well, despite the fact that it's not 100% identical, it helps you uncover end-to-end plumbing issues, such as the interaction between the cloud and the device, or the device and the notification, or the sensor and the motion detection. End-to-end plumbing issues can easily be figured out for this. Server-side bugs, cloud processing bugs of the clips that were sent to the cloud, what we missed out, what we didn't, easily figured out. We identified memory leaks, CPU utilization, temperature over long runs of time. When motion happens over continuous periods, how does it behave? And all of this is historical data that we store so we can compare these metrics to last week, last month, what happened in our previous build. The camera simulator is there to basically come up with our secret sauce. So we have all of our raw camera data, thousands and thousands of video. And this is raw camera data that we don't have to play back into the camera from the camera, because all of this is stored in the cloud. So we can, and it's all obviously internal data, not production data. And we can play it into our motion detection algorithm and say, hey, from the curated data that we had, what are we doing? How many events are we missing? How many are we catching? Is there false positives that are happening? And this gives us our secret sauce of coming up with the best precision and recall curve. The A/B testing is an in-house solution that we created for comparing different metrics. So as mentioned, the precision recall curve is a trade-off between false positives and true catches. Obviously, we don't want to miss we don't want to catch all of the events, because that will give us a lot of false positives for a user. So it's a thresholding. So 2 different versions. We created 3D stands that we gave out to internal Googlers and nesters, and said, hey, take it home, and if you're not concerned about your privacy, we're going to scrape your data. And what we do is we put these in indoor, outdoor, all these scenarios and situations that are relevant to the user, and we scrape the data. So the field of view is exactly identical, because we created custom 3D stands that make the field of view exact, and we have a wide field of view angle, so it doesn't really make much of a difference. First of all, we compared the overall metrics. Hey, were there any major known issues, or did something go wrong with memory usage, CPU utilization time, internal metrics that we have? If all that looks good, we quickly do a time series merging data. What that does is merges both of the notifications that came up from both cameras into a single notification list. And we start traversing through that list to identify a difference between the camera notifications, which map into alerts. As soon as we identify them, it comes down from 800, 900 clips per camera to just 2 or 4. And these differences, we manually go through them because it gives us valuable insights and say, what are we missing? What are we catching? Why is it doing better? Once we have that, we can train our algorithms again to say, hey, this is motion you want to catch on, and this is motion you want to miss on. And if the precision recall curve and all of the other stuff that we mentioned, if it all looks good, we ship our feature. And that's why it's a continuous loop of continuously improving our motion detection with the system. So coming to our conclusions, hardware is hard, as we saw, but that doesn't mean that we shouldn't do it. What we have demonstrated is only a small subset of our testing paradigm. Automation has helped us save time and caught bugs. It's provided repeatability and gotten rid of subjective items such as motion detection from human bias and error. And of course, we're always looking for help. So if you're interested, come talk to us. Thank you.
Before we go to questions, I have one administrivia. Rousi from Splunk, if you're around, please go see the AV guy so you can talk next. Get mic'd up. Now, questions for you guys. Can you speak how you test security on these devices which are becoming part of the family?
No.
Well, that was straightforward. I think I know the answer to this one, but I have to ask it anyway. Can you guys help GTAC's room fix AC temperature?
You'd have to install Nest thermostats first.
So possible, but
Sure.
not immediate.
Yes.
Sign up for field trial.
Most of the Nest products require Wi-Fi. If internet service goes out, are Nest devices smart enough to know when to reset the device? How do you test these types of scenarios?
So that typically falls to our communications integration engineering team. So many of the devices we build are just used specifically for device testing, right? Platform device testing. And then a lot of the interconnected tests or wireless tests are all run by our communications and integration team that I really have no idea about.
So you guys just aren't the experts on that particular area. Okay.
But the camera, I can say, yeah, we have some sort of logic that kind of understands when the power is out or when the AP is down. So we have some sort, we have internal tests that we can do for that.
Okay. For motion detection, how do you... I lost my screen. For motion detection, how do you effectively distinguish between people who should enter the house and unwelcome visitors?
I can't really go too much into detail about how we do that. Yeah, it's one of those secret sauce things, but
I think they told us all they can.
But one of the things about motion detection is very subjective. Some people like shadows. Some people don't want alert on shadows. Some people want notifications on cars passing by. Some don't want it. So some people want lights turning on. Some people don't. So a lot of it is very subjective. So things that are like have difference of opinion, we kind of keep to the side when we're testing. We just kind of like on the side just measure this is how it did. But we usually go for things that everyone usually agrees that this is what we want to alert on. For example, a person walking by in front of you, you want to be alerted on that. Or in front of the camera. So we try to eliminate things that are difference of opinions when we go out.
Cool. And you might be able to answer this. The question actually specifically asks, how do you ensure smoke detectors aren't flaky, but how do you ensure any of the hardware that you test isn't flaky and like sending false positives and turning up the heat or setting off a smoke alarm?
Yeah, so I mean, this is all a part of larger testing schemes, right? So we talked specifically about some features, but there are also the hardware teams all run lots of heavy validation on their prototype hardware and through every build. And then we have reliability teams that are constantly running reliability tests is the best way to describe it. We've built, I mean, especially for smoke detectors, we've built things like dust chambers and bought smoke chambers to run accelerated life testing and really try to make sure that people are trusting us enough to put these devices in their home, and we certainly don't want to lose that.
Cool. Well, thank you guys. I now want to automate my home.
Thank you.